Hello friends, welcome to the mathematical room. I'm your caretaker. So this is a continuation of the previous video on set theory. So in this video we are going to solve some problems on set theory, and also if you remember in the previous video we did not prove all the properties that we have discussed. So in this video we are going to finish proving those things. So let us first start with them. Okay, so let us recall the properties that we did not prove. If you recall, the properties of union we have proved all of them. However, for intersection we actually haven't proved any of them. I have just simply mentioned that in place of or we have to use the properties of mathematical logic involving the logical connective and. Okay, and I left it to you to prove all these things. So now let us finish those things. So the properties, as you can recall, they were, the first one was commutativity. For two sets A and B, their intersection is commutative. So this this goes along the same lines as the previous proof of commutativity of union, but nevertheless, for the sake of completion, I'll carry this out. Okay, so the proof goes like this. Let, by now you already know how to prove these things. You have to show that this is a subset of this and this is a subset of this. So that's just what you have to do when you want to show that two sets are equal. So we assume we start by assuming an element in the first set. So this implies, okay, I keep on writing let. If you write let x belong to A intersection B, then you have to write a full stop here. That sentence ends. And then you have to write then x belongs to A and x belongs to B. Otherwise, you don't write let. Okay. In mathematics, we use the words let, assume, define so often that it becomes a bad habit of starting everything with them. So you just start like this, x belongs to A intersection B. You don't have to write anything else. So the solution or proof, this is rather a proof of this fact. It can be started like this because this is a legitimate statement. It says that x is an element in A intersection B. So this implies x belongs to A and x belongs to B. So just like before, we can switch these two simple statements in this conjunction. We can write x belongs to B and x belongs to A. This is because of this property. Since P and Q is equivalent to Q and P, although we are using only one part of this equivalence. Which one? This one. Okay, for us this is P and this is Q. So this again, by the definition of intersection, this implies or this means x belongs to B intersection A. Okay, so this is your argument. Now once the argument is over, then you can write hence A intersection B is a subset of B intersection A. Okay, in an actual proof you have to write all the steps. Okay, then after that we want to show that this is a subset of this. So you start by assuming an element in B intersection A, and it goes pretty much the same way. This implies, you see, sometimes we write statements which are implications. I mean, this is a sequence of implications, right? Sometimes we write them in a vertical form like this. We write each statement in a separate line, and we sometimes show the reason why the implication is true alongside the statement. I mean, for example, from this statement, you are getting this statement. So at the end of this statement, you will write the reason for getting this statement from the previous statement. Okay, so that's how we sometimes write. But at the same time, we can also write it just like we write sentences in a paragraph without writing like this. For example, I have taken y in B intersection A. I can write implies here also. That is also true. Actually, this way of writing helps you write all the statements properly so that you get more horizontal space to write a single statement, so that when you see the proof, you can see one statement at once instead of seeing it in a paragraph, which makes it somewhat difficult to see at once. So this style of writing is better for the purpose of visualizing the thing, what is going on in the proof. However, to save space, or if you ran out of space and you still have to write something, you can keep on writing like a normal paragraph. Okay, so having said that, we write y belongs to B, and so here I have to come to the next line, and y belongs to A. This makes it somewhat less appealing to see than a statement which is written like this. Nonetheless, there is no logical difference. Okay, it's just simply a matter of how you want to present your proof. Ideally, things should be written like this. Mathematical arguments should come in the center, that too. Okay, so y belongs to B and y belongs to A. This implies again, now again we are going to use 1/2 of this equivalence, this one. But this I am writing this only for showing you, okay? We cannot write that thing here. Y belongs to A. So we switch the two statements. We write y belongs to A and y belongs to B. But you see the problem of writing like this. You can insert a reason like this here, but it looks somewhat cumbersome and not so neat. Okay, you can write here also, you can write since. By the way, if you simply write this, it does not make sense. You have to write for any statements P and Q. Similarly, you can write the other one here. Actually, the other one is also simply the same thing. If you treat this as P and this as Q, then the same thing is the reason for getting this one here also. So you get the point why this is happening, and this again implies y belongs to A intersection B. Hence, B intersection A now is a subset of A intersection B. Hence, B intersection A is, oh, I have already written this. Okay, now if you write these things in the center, like this. For example, hence instead of writing it in one line, you write it in the next line, in the center of the line, the center of the page. You can then number this. You can write it as relation 1, this as relation 2, so that you can refer them easily. Ultimately, using these relations, note that this is not an equation. In equation you have equality sign. This is not an equation. It is something like an inequality. I have already discussed about this, that when it comes to sets, just like numbers, in numbers we have equality and inequality. In sets also we have equality, but in place of inequality we have the subset relation. Okay, so from these two relations, or you don't write anything, from 1 and 2, we get A intersection B is equal to B intersection A. And this ends the proof. Hence, proof, that also you can write to indicate the fact that the proof is over. Right, so this is how an actual proper proof has to be written, including all the details. Okay, don't leave anything to imagination, not to someone else's imagination, not to your imagination. First of all, you have to know exactly why each step is valid. Then you can explain it to someone. It is better to either provide all the details or write something which supports the steps you have taken in the proof. Next one is, as you already know, associative law. Now, since I have shown one format of a proof, I am going to be sketchy with the rest of the proofs here. Okay, I am not going to write formally everything. I will just show the steps and you fill out the rest of the things. Okay, now I have to show, first of all, I show this is a subset of this. So I take an element here, A intersection B intersection C. So this implies X belongs to A and X belongs to B intersection C. This further can be broken down like this. X belongs to B and X belongs to C. This implies, okay, now this is of the form P and Q and R, where P, Q and R are statements, valid statements. Need not be mathematical statements, any statements, but here we have something like this. Okay, and this is equivalent to P and Q and R. This is coming from the fact that conjunction of statements itself is associative. From that law, we are going to use this law here in this situation because it is of the same format. And we use only one half of the law. So this we can write as X belongs to A and X belongs to B. You will notice that although many proofs in set theory are somewhat similar to the other proofs in set theory, but you have to practice writing these proofs more and more, because just looking at something or looking at someone solving a problem or carrying out some mathematical argument, you will not really feel the obstacles that one comes across when one starts to do these things by hand. Okay, the so-called getting your hands dirty. You have to actually do that yourself. Okay, do that on your own. Then you will feel the difficulties that we encounter while we perform such an activity. And then when you try to overcome those difficulties, you gain experience, and that counts a lot. You see, in mathematics, we often come across this type of proofs, which for which the procedure or the arguments that we have to carry out, they are known beforehand, or you have at least some guess of what you have to do. But in real mathematical problem, I mean the problems that mathematicians are concerned about, they don't have, at the beginning, they don't really have any idea of what to do. They have just some vague idea of what is going on. Then they feel like this should be a result. Here you know that something has been asked to prove, so you know beforehand that it is true, and it has to, you have to proceed in this way, that you have to take this set, show that it is a subset of this, and vice versa. That way you can prove. But sometimes that path that you have to take, that is not clear. So then what does the mathematician do? He or she will recall things from experience, and that will help the person formulate some strategy. Okay, so although the proofs look same, but keep practicing, keep writing them. Okay, and every time you do something, always never write anything mechanically. Always try to understand yourself why you have written something. Unless you do that, you will quickly get lost, and you will lose track of what you are doing, and then things will start to veer towards nonsense. Anyway, so in place of this we can write this, and x belongs to C. Now combining these things back, I mean writing them in more compact form, this means A intersection B and x belongs to C. This can further be written like this: A intersection B intersection C. We have thus proved that any element in this set is again here. So, and as I have already said, or we have discussed, that this can be done in the other direction also. If you take an element in this set, that implies this, this implies this. Now, if you are writing double implication, actually you can carry out a proof like this. For that, you write since. Since these statements are equivalent. You see, now from here you go to this. That's why I have written this direction of the double implication. Now from here, if you have to go to this one, then you have to include that one also. Okay, because here you are actually using the fact that P and Q and R is equivalent to P and Q and R. Okay, so then the rest of the steps are easy. Since any element belonging to this set is equivalent to that element belonging to the set, equivalent, okay, not just simply implies, comma, we have these two containments, A intersection B intersection C is a subset of A intersection B intersection C and the other way around. A intersection B intersection C is also a subset of A intersection B intersection C. If I continue from here, hence, by the principle of extensionality of sets, these two are equal. Although we don't write that, we know. Okay, some things which are extremely obvious, they are not written, not more than once. But in the back of your mind, everything should be there. So that if someone asks you some doubt, you should be able to clear that doubt. Hence, A intersection B intersection C is equal to this. Hence proved. Or therefore the proof is over. Right. So after this we had some minor results which don't have names like this: commutativity, associativity. The third one, since they don't have names, they are difficult to remember also. What was it? Oh yes, A intersection empty set is equal to empty set. This is 3. A intersection A is equal to A. A intersection B is a subset of A, and also A intersection B is a subset of B. So these are the things in the third subdivision, or the third property or set of properties. Now you see, to prove this one, you already have this. Why? Because the empty set is a subset of every set. So in particular, the empty set is also a subset of A intersection the empty set. So you can write like this: we already know, or we already have this. So one half is given to us. For the other half, you take an element x in A intersection the empty set. Okay. Oh, actually, to prove that something is a subset of the empty set, what do you have to do actually? Suppose there exists an element x belonging to A intersection the empty set. Okay, you can ask me at this point why I did not write in the usual way I do. For example, let x belong to this and then carry out the argument, ultimately getting that x belongs to the empty set. Why I chose to write something different? Suppose there exists an element. That is because had we taken the usual path, we would not get anything. How do I know that? That comes from experience, that comes from practice. Okay, so when you in general see solutions to mathematical problems or proofs, you may wonder why a particular step is taken. There is no short answer to that question. You just have to understand that the steps have been taken because they work, and behind these steps there are many failed attempts. People have taken many paths, they led to dead ends. Then finally they found out some path which led to the conclusion of the result. Okay, so obviously the failed attempts do not form a part of the proof, but that is important. Now you have to follow those failed paths yourself. That is called the struggle. If you don't struggle, then you will never realize why something is done. Okay, anyway, so having said that, we have done something slightly different than our usual strategy of considering. I mean, we have showed that this is, I mean, already we know that this is a subset of this. We then have to show that this is a subset of this. Now, instead of taking any element x in this and showing that x is in empty set, we have expressed a doubt here. We have supposed that there is an element x in this. This is actually, this part is proof by contradiction. Whenever you see suppose or assume this sort of words, most often what we are trying to show is exactly opposite to our supposition. We have to show that the supposition is wrong. Having supposed something, if we run into some difficulty or if we run into some nonsense, then that means the supposition could not have been correct. So that way we prove that the supposition is wrong. Now, what I have to prove here is that this is a subset of this. Now, this is a subset of this means what? Empty set already has nothing in it. So if you have another set, suppose this is the empty set, it has nothing in it. If you want another set to be a subset in this, that set must also be empty, right? Because otherwise, if this set has some element, that element will come inside the empty set also, contradicting the fact that it is empty. So that's why we have supposed that there exists an element here. We are going to show that that is not possible. Thereby, we will prove that this set is also empty. Okay, that way we will get the result. So x belongs to A intersection the empty set. What do we know from this? Then x belongs to A and x belongs to the empty set. This is coming simply from the definition of intersection. Now what about this statement? This statement is a conjunction. P and Q. P and Q. If you recall from the definition of conjunction from mathematical logic, when is a conjunction true? When both P and Q are true. If you look at P, we don't really know whether P is true or not, since A is, we are not sure about truth of P, just as it is. But Q is false, because no element can be in the empty set. Empty set has nothing. So Q is false, that means this P and Q is false. Okay, this conjunction is false. So that's what you write, but this is not possible since x belonging to this is false. So our supposition is wrong. So our supposition is wrong, that is, okay, I have just now noticed one thing. I'll tell you. So our supposition is wrong. What was our supposition? Suppose there exists an element in this set. That is, this set has no element. There cannot be any element in that set. In other words, this set is empty. Do you remember we have proved that there is only one empty set? So we have proved that this is an empty set. But since there is only one empty set, this set has to be that empty set. Okay, so that lemma, unknowingly we are using that. Now the thing I have noticed here is that we actually don't need this part. Do you see that? We have proved that this is equal to this. We don't need a weaker statement than this. So instead of starting the proof like how we have started, you start it from here. So this is a slightly shorter proof. Actually, it gets the job done. So this way you can see that you don't always have to, like a robot, you don't always have to show that this is a subset of that, that is a subset of this. No, you have to understand if the proof can be made shorter, then shorter means better, provided you don't leave out details in the proof. I mean, you don't leave out anything. This one, however, is it is similar to the same thing with union, idempotence. So we start as usual. X belongs to A intersection A. This implies X belongs to A and X belongs to A. Oh, I should not write full stop. See, this is a running statement, okay? You don't write comma or full stop, anything here. This is a single statement. This implies this, implies this. At the end, you can write full stop, but if you write this whole set of arguments in the middle of a page, usually we don't write any full stop or comma or anything. Okay, now in place of this, I am going to write X belongs to A. What is what is the reason for that, or what is the justification for that? This is coming from the law of, well, not the law of simplification. It is coming from, no, with and we cannot, can we simplify with and? P and Q. See, I forgot. P, or although this is not related to this, but what is law of addition? I mean, what appears in law of addition? Conjunction or disjunction? P implies P or Q, yes. Disjunction. And in law of simplification, conjunction appears. But these are not the laws that we need here. Here we have that idempotence, P and P, because both the statements are the same here. Implies, actually this is equivalent to P, but we at this point we need only one. Here we can get by simply by writing it like this. We also use the other direction. X belongs to A implies this. Now then we have to write this. Okay, this. Since this, we have A intersection A is a subset of A and A is a subset of A A intersection A. So these two containments imply this. These are equal sets. To prove this one, A intersection B is a subset of A. Here just you have to prove that a set is a subset of some other set. So you start by taking an element in the smaller set, supposedly smaller set. So this implies X belongs to A and X belongs